Okay, so now now let's start the chapter 2. Okay, in which we basically study the atoms, electronic configuration. Very powerful topic this is. Okay, I like this topic. So we will study here the atoms and the electronic configuration in this chapter. Okay, let's start this. Okay, so the elements, substance, and the mixture. Okay, so let's first of all tentatively classify the matters. Okay, matter can be either pure substance, you see, or it can be a mixture of or a combination of two or more pure substance. For example, iron, it is a pure substance, just the iron it has. But if you think about the water, it has H2O, right? H2O means two hydrogen, one oxygen. It's the mixture, basically. It is a combination of two different atoms. Okay, so the general mixture also you could have. For example, you can mix water and oil. However, they are not good miscible. Sugar and the water, that is also a mixture. Okay, sand and the sugar, that is also a mixture. Lots of mixtures. Okay, so the mixtures are basically physically separable into pure substance. Okay, you can separate the mixture into pure substance if that is a mixture, right? However, the homogeneous or heterogeneous, there are two types of the mixture, but that can be separate into the pure substance. So pure substance either can be element, you see, either can be that is element. Okay, so either the pure substance can be element or it can be compound. Okay, so pure substance can be pure substance, either it can be element, okay, that cannot be further subdivided, and or it can be compound, means the combination of two or more than two elements. Okay, so this pure substance one is the element, and that element you cannot further subdivide that. And other pure substance is a compound, for example the water, you see, this is also a pure substance, but that is a compound. Okay, so in this case the elements are mixed in a fixed ratio, and they are mixed in a fixed ratio, and after mixing they form a compound. However, later on you definitely can separate this. For example, electrolysis, you can do the electrolysis and you can separate hydrogen and oxygen from the water. Okay, so that is the pure substance. The mixture can be further you can divide in two types: homogeneous mixture and the heterogeneous mixture. Okay, so what the basically the homogeneous mixture means, let's give me start from the example. Okay, let's say this is one substance. Sorry about this bad picture, not a very uniform good picture. Now let's see, this is another. Okay, this is substance A, substance B, both are mixture. Okay, and now let's see that here how they are mixed. So how they are mixed, let's see that. They are mixed like that. Okay, red, so they are mixed by red. Okay, red, and again they have the blue also. Okay, they have the blue. See, this is the mixer one, and you are doing the measurement in different part. In this corner, for example, you take some sample from here and you get one red and one blue, and at this corner also you get one red and one blue. Anywhere you pick out from here or pick out from here or pick out from here, wherever, it doesn't matter. From that sample you pick out something. okay, some 1 gram or 2 gram. And if you see that what are the constituents of that, if you find out for example this corner 1 red, 1 blue, this corner also 1 red, 1 blue, whatever, wherever you pick, wherever you sample select, every place you find the same composition. Okay, that is the one thing. And other thing is, for example, you measure the pressure here, you find the 1 atmosphere, you pressure here, pressure here, pressure here, anywhere all the properties are same, equally distributed. Okay, the chemical constituents are also equally distributed. So from any portion equally distributed, then they are said to be the homogeneous mixture. For example, salt water, you can take the salt water from one corner, you will be feel that is a salty, other corner you will feel salty, other corner you will feel salty. Okay, so every particles or every constituents are equally distributed, homogeneously distributed, that is said to be the homogeneous mixture. But if not homogeneously distributed, for example, you search from here, you get the 3 blue, 1 red, you search from here, you get 2 blue, 5 red, not homogeneous, right? Different place has different distributions. For example, sand and sugar. Okay, if you mix the sand and sugar, it's not guaranteed that one corner sand and sugar give you how much sugar, and the other corner sand and sugar you give the same. It doesn't matter, it's the heterogeneous mixture. So it is said to be the heterogeneous mixture. Okay, if equally homogeneously distributed among the mixture, if all the particles are all the member particles are homogeneously distributed, that is the homogeneous mixture. Okay, if not homogeneously distributed, that is a heterogeneous mixture. So this is the matter. Now let's again classify further. So element, okay, we have classified previously element and a compound, right? So what is the element? Element or substance, for example, carbon, hydrogen, iron, oxygen, neon, nitrogen, etc., that consist of identical atoms, they are said to be the element. Okay, for example, if you have a glass of oxygen here, if you have a glass of oxygen, you will have O2 here, O2 here, O2 here, O2, same type of the elements. So same type of the identical atoms. Okay, so O2, this is oxygen, this is oxygen, these two are identical. So such things are said to be the element. So there are how many elements? There are 180 known element. Okay, so of these 98 occurs in the nature, the others have been made by chemists and physicists. In the nature you have 98 elements, and the remaining elements are made by the scientists. Look at that, how tremendous work, right? Human being, we can make the elements. It's very interesting, right? The Day symbol consists of 1 or 2 letters. Some elements symbol are just a single letter, some elements symbols are we take 2 letters. For example, hydrogen, we just take 1 letter. Oxygen, we just take 1 letter. Nitrogen, we just take 1 letter. Carbon, we just take 1 letter. Okay, so these are 1 letter. Sulfur, we take 1 letter. But let's see that calcium, we take 2 letter. Aluminium, 2 letter. Nickel, 2 letters. Sodium, 2 letters. Silver, 2 letters, right? So some elements we just take 1 single letter, the first letter of its name, and some we take the 2 letter. Okay, so name are derived from the variety of the sources. Okay, the English name of the element, people important in atomic science, geographic location, planets, mythological sources, etc. When the scientists give their name, the elements are named by different way. Okay, some are the English name, English people's name. Okay, and some are the important people. For example, the curium, you know, curium, some place, americium, for example, francium, for example, right? That are from the some place name. So some mythological sources also. Okay, so planets also, plutonium for example, planet, right? So these elements are named by variety of words. Okay, so so that's the naming of the element from either simple English name, these metals in English name, or these are some elements are named by the planet, some named by the important persons, right, scientists and like that. Okay, some are countries also, francium for example, right, like that. Okay, so that's it. Now compound. The compound is also a pure substance that is made of a different type of the element. For example, if you think about the S2O, it is a compound because it is one oxygen and it has a two hydrogen. Look at that. So different, right? These all atoms are not identical. It is not as like the S2, right? Okay. So this is different type of the compound, but this is also pure substance S2. Okay, but this is compound. Compound are made up of two, or compound are made up of two or more than two identical or different atoms. Okay, for example, so S2, it is also a compound molecule, right? So pure substance that is made up of two or more elements in a fixed ratio, 1:1 ratio. And there is another compound also, S2O. Okay, so its ratio is what? 2:1, means 2 hydrogen 1 oxygen, but this is 1:1. Okay, nitrogen, right, 1:1. Okay, sulfuric acid for example, H2SO4. look at that, 2 hydrogen 1 sulfur 4 oxygen, like that. Okay, fixed ratio. And the formula of a compound tells us, these are the formula of the compound. Okay, formula. Now let's see the formula. Formula of the compound tells us the ratio of its constituent element and identifies each element by its atomic symbol. Okay, these are the formula. Okay, the formula are written by the element symbol with the fixed ratio. Okay, and these elements are the symbol of the elements. Okay, so for example, S2O, this formula tells us that the ratio between two elements, okay, hydrogen is to oxygen is equals to 2:1. Okay, for example, H2SCl, and that will be hydrogen ratio with Cl is equals to 1:1, right? So now if you think about the H2SO4, you can write that as a what? 2 hydrogen, okay, sulfur, oxygen, right? How many hydrogen? 2 hydrogen and 1 sulfur and 4 oxygen, right? So like that. Okay, so sodium chloride for example, sodium chloride means sodium and chlorine, sodium and chlorine, right? Sodium is 1 and chlorine is also 1, so that is 1:1. So these are the formula of the compound, and the compound are combination of 2 or more than 2 elements, but these elements can be identical also. Okay, so now let's see the structure of the water molecule. Okay, so see that, look at that here, representation of water molecule. Okay, in the chemistry, how many ways we can represent? One is we write H2O, that's that. Okay, so look at that, just we write the symbol of the letter symbol and their ratio. This is 2:1, right? 2 hydrogen 1 oxygen, so with ratio. And other is we write like that, little bit structure. See, this is line, so we just represent what is connected with what. We know that. So in H2O, look at that, in H2O, is that true? O, no, hydrogen and hydrogens are not connected, but both hydrogens are connected with oxygen. So that's why connection it will give you. So little bit further is, this is, see that ball and stick. One ball is here, red ball, okay, because the oxygen is generally in, we saw in the red color. So okay, red ball is here, and other is the white ball is here, okay, that is the white ball. Okay, let me make this this color, white ball, blue ball, and other is blue. This is said to be ball and stick, ball and stick. And there is other is the space filling. Okay, so it will show, you can show that space, big space, and a small hydrogen, other small hydrogen, that is the space filling. Space filling way, different way of writing the formula, writing the structure. This is just the one way, okay, and this is another way. This is said to be the line linear representation. Okay, we connect these element by the line, second, and other is the ball and stick. Okay, so different color ball, different element has different color ball, we use that. For the oxygen we use red, for the hydrogen we use white, and like that. And third is the space filling, means that what could be the space occupied by this element, but the color is same. Okay, if you see that this is the, this red color space, this is the oxygen, white color space, that's the hydrogen. That's the another way of representing the molecule. So now let's again go to the mixture. Okay, a combination of two or more pure substances, that is the mixture. The substance may be present in any mass ratio. In the mixture there is no fixed thing. Okay, so for example, in case of the compound, you make H2O, here is fixed, 2 is to 1, but in case of the mixture any ratio can be. Okay, you mix the sugar and water, no, not necessary 1 is to 2, 2 is to 1. 2 kg sugar, 5 liter water, 2 kg sugar, 100 liter water, anything can be. Okay, so each substance has different set of the physical properties. Sugar has different physical property, water has different physical property, right? They have different physical property. Mixture may be homogeneous or heterogeneous. We last time say that. Okay, if we know the physical property of the individual components of the mixture, we can use appropriate physical means to separate the mixture. Okay, so however we can separate the compound also using the energy, but the mixture we can use a different idea to separate the mixture. Okay, for example, distillation. Okay, different type of the distillation, many type of the distillation. Okay, similarly decantation, etc. Okay, gravity filtration is also one method. There are many methods by which we can separate the mixture. For example, okay, heat separation, we can, distillation we can do that. Okay, distillation means we boil that, and the different things boil in the different temperature. That's why we get benefit of that fact and we separate them. Okay, so now next go to the atom. Now guys, now let's say start with the atom. Atom is the smallest unit of molecules. You can say that. Okay, smallest unit of matter, or even the smallest unit of molecules also, atom. Okay, so we will discuss here the Dalton's atomic theory. Okay, because the different scientists has given different theories. We have a Bohr model. Okay, we have a Dalton's method. We have many models, successful models. Okay. We have the atomic models. What atoms looks like, what is the atom, what is the smallest thing looks like, that the scientists thought from, look at that, 1766. very long ago, right? 1766. Can you imagine? Since then, the Daltons give one theory. Okay, so what Daltons say that all matter composed of very tiny, indestructible, indivisible particles, which Dalton called atoms. Dalton gives the name of these smallest particle as an atom. Okay, what he say that all matter, for example, if this is a matter, it is composed of very tiny, indestructible, you cannot destruct them, you cannot destroy them, indivisible, you cannot further divide them. Okay, for example, you can cut in 4 half and this cut 4 half, then cut 4 half, then cut 4 half, right? You can cut the matter, but the atom is the smallest unit, further you cannot divide that. Okay, and that is said to be the atoms. That name was given by the Dalton as atom. Okay, other is what other Dalton's theory say, all atoms of the same element have the same chemical property. Atoms of the different element have different chemical property. Yes, what he say that if you have an element A, its atom has different property, but these all atoms have the same property. Okay, other element B, for example, this element B has the different atoms, and all of the atoms which that B makes, they have the same property. Of course, that's true. For example, if you have an iron block is made up of the iron, right? And these all irons are identical. Okay, but iron's atom is totally different than any other element's atom. Iron is an element, iron is, right? Its atoms all will be identical, and similarly others also identical. Hydrogen, all hydrogen atoms will be identical. Okay, so now the other he says that, okay, compound. So he again say that compound are formed by the chemical combination of two or more of the same or different kind of atoms. So Dalton says that these tiny atoms, right, atoms, and he say that compound, actually that is true, compound are made by the chemical combination. Okay, chemical combination of one or two or more of the same or different. Okay, two, at least two needed, right, to combine. Okay, two or more, they could be same or they could be different, same or different. Okay, more of the same or different kind of the atoms. Yes, that's true. For example, nitrogen gas, let's say nitrogen gas, this is made up of two same element, right? And but the hydrogen H2O, you see that HOH, right? So two different type of the element, but here two similar type, here two different type. Okay, so that's why same type of element can also form, combine, and that also can be the compound, or different type also can be compound. So again, the molecule are tightly bound combination of two or more atoms that act as a single unit. Yeah, very nice. What are the molecules then? Molecules are tightly bound, tightly bound combination of two, look at that, two or more atoms that act as a single unit, right? So yes, they are very tightly bound, and that as a whole combination act as a single unit. Similar property, for example, oxygen and hydrogen, water, see, different chemical bound very tightly. Okay, and this is the combination, this is one combination, this is one water molecule, then other water molecule. So the water molecule will have different property than other, and this will become a single smallest unit. So that's the Dalton say. So now, what was the evidence of the Dalton's law? Okay, Dalton's told that. Okay, he gave the theory, but what are the evidence? So there was another law, which is the law of conservation of mass. Okay, law of conservation of mass. Law of mass. It is similarly as like the law of conservation of energy, but let's say it is conservation of energy. So conservation means something conserved. Okay, so mass, look at that, what say that mass can be neither created nor be destroyed. That's the law of conservation of mass. As Dalton explained, if matter is made up of the indestructible atoms, then any chemical reaction just changes the attachment among the atoms but does not destroy the atoms, right? Yeah, laws of conservation of mass also proves the Dalton's theory, because so if matter is made up of indestructible substances, then chemical reaction means just the attachment are different, but the atoms never gonna destroy. For example, let's say carbon monoxide, okay, plus lead oxide give you carbon dioxide plus lead. So carbon monoxide is CO, one carbon, one oxygen, plus lead oxide is PbO. Okay, PbO, that will give you CO2, okay guys, plus Pb. So what's happening here? Carbon monoxide, carbon is not gonna destroy, carbon is carbon as it is, plumbus or the lead is lead as it is, right? Oxygen is oxygen as it is. Only what is happening here is CO attachment is here is PO attachment, but attachment become different, right? So PO, this oxygen attached to with this carbon here, right? And this become liberated Pb. So only the attachment are different. It means that yes, Dalton was correct. So law of constant composition, there was another, and it say that any compound is always made up of element in the same proportion by the mass. Yes, so that is the law of constant composition. So all compound is always made of element in the same proportion by mass. For example, as 2O is decomposed, we will always get 8 gram of oxygen for 1 gram of hydrogen, you know. So always, it doesn't matter you break the oxygen water today or tomorrow, it doesn't matter, water from here or water from other place, if you decompose that, you will always get 8 gram of oxygen. You will always get 8 gram of oxygen, okay, 8 gram oxygen for 1 gram of hydrogen, okay. Always in this ratio, if you get 16 gram of oxygen, you will get 2 gram of hydrogen, like that, 8 gram of oxygen for 1 gram of hydrogen, you are always getting that. So that also verifies. Okay, now let's think about the different type of the elements. Okay, so now monoatomic, diatomic and polyatomic elements. Okay, mono means one, di means two, poly means many. Okay, so monoatomic elements means consist of single atoms. For example, helium, it has only one atom. Okay, so single atom, for example, helium. Diatomic elements means there are several elements that occurs as a diatomic molecule. Okay, you know, diatomic molecule means two similar or dissimilar atoms, okay, combined together and form a molecule. For example, S2. Hydrogen element you will find in this form. You cannot find the hydrogen in a single hydrogen atomic form, but you will find the molecular form. Okay, so nitrogen for example, similarly oxygen for example, fluorine, chlorine, bromine, iodine. Okay, so Br2, chlorine, like that. So these are the diatomic. So polyatomic elements, I'm not saying about the compounds. Okay, I'm not saying about the mixtures or compounds, I'm saying about the elements. These are the elements, they are not the compounds. Okay, so S2, N2, same thing, they are the elements, pure substances, but they made up of the same kind of the atoms. Okay, they are diatomic. So you have a triatomic also, for example O3, ozone, phosphorus, okay, S8, they are the polyatomic. So it has more than 2, it has 4, it has 8, like that. Okay, these are the polyatomic elements. Some elements, okay, so diamonds has millions of the carbon atom bonded together to form one gigantic cluster, and we have the cluster also. Okay, so that is also an element, you can assume that. Okay, so these are the types of the elements. Okay, element, not only the hydrogen, element can be molecular form also, element can be, okay, multi-atomic, okay, diatomic or triatomic or polyatomic, right? And that kind of element can be also found. So the how the atoms is made. Okay, atom is made, for example, this is okay, so how the atom is made. General concept is atom is made up of one nucleus, and outside the nucleus there are cells. This is the very simple model of the atom. Okay, so outside the nucleus, this innermost core is said to be nucleus, and these all outside region is said to be the orbitals or cells. Okay, so nucleus has most of the mass is inside the nucleus. So whatever the small particle that constitutes the atom, they are said to be the subatomic particle. Okay, subatomic particles. Subatomic particle means those particle makes the atom. Okay, the particles, those make atom, and basically they are three. Okay, they are basically proton, electron, and a neutron. They are basically three. Okay guys, so how we study this proton. Proton symbol is P, neutron symbol is N. Okay, similarly, let me see that. Okay, proton symbol is P, then neutron symbol is N, electron symbol is E, generally E minus. Okay, so they have a charge. Okay guys, they are assumed as a charge, or they have charge actually. Proton attract a electron, that's why electron we think as a negatively charged, and proton we think as a positively charged. That's why this is positively charged. Electron is negatively charged always, and the neutron is zero charge, chargeless, no charge. Neutron is. Okay, so how much charge we assume that? Proton we assume +1, neutron we assume 0, electron we assume -1. Overall is 0. You see, overall is 0. So what is the mass of protein? The proton, mass of proton. Mass of proton, look at that, how much is small in the gram. Okay, it is in the gram. Mass of one proton is how tiny that is. Okay, 1.6726 times 10 to the power minus 24 gram. Look at that, how much is small, right? Minus 24 gram. And electron, this is the proton. Mass of neutron, it is also about the same thing. It's a similar, okay. 1.6726 times 10 to the 24 gram. And the mass of electron, okay, mass of electron is very small, about 2000 times lighter, means that less heavier than either neutron or proton, okay guys. So it is 1 times 1 by 2000, 1800 something actually, but let's see, 2000 times mass of proton, okay. And that number is this, look at that number is actually 9.1094 times 10 to the minus 28. Look at that gram, how much is small it is, right? So electron's mass is very, 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 very small. So you can neglect that in when you calculate the atomic mass, okay. We will discuss that later on. So now these are very small number, very large exponent value, right? So that's why these are very big numbers and very small numbers, right? Both big and small. So that's why there is another unit to measure the mass of the subatomic particle, which is said to be AMU, atomic mass unit. Okay, AMU, atomic mass unit. So proton is +1 AMU, or 1 AMU, sorry, okay. Proton is 1 AMU. 1 AMU means how much? 1.6726 times 10 to the minus 24 gram. 1 AMU means, okay. So and the neutron is equals to also 1 AMU, and the electron is equals to 0.0005 AMU. Look at that, okay. So AMU is the atomic mass unit, okay guys, don't confuse it. So AMU is actually 1 AMU means this much. 1 AMU means 1 AMU equals to actually 1.6726 times 10 to the power minus 24 gram. So this is a big number, that's why we write this whole as a 1 AMU, okay. So that's about the subatomic particles. Now let's go to the one atoms, which is what the atom looks like, typical atom. Let's see here. First of all, we will see that the relative size, okay. So now this is atom's nucleus. Atom has two parts, okay guys. One is nucleus, in which you can find the proton and the neutron, okay. Nucleus in which you find the proton and the neutron. This is the nucleus, okay. Proton and a neutron, you find that nucleus. And outside that, okay, space occupied by the electron. This is the region, that region occupied by the proton and the neutron. This whole region, they occupy that, okay, proton and neutron. So outside that there is a space. It is a space, okay guys. The region outside the nucleus, this is a nucleus, it's the outside. Here is outside region, okay. For example, my head is nucleus, whatever the region around my head, that is the place for the electrons, okay. That's the house of the electrons. Electron can be found here in this region, and in this core region proton and neutron can be found, okay. And outside that, electron found. So what is the size? Look at that here. Whole one atom is about angstrom scale. Angstrom is 10 to the power minus 10 meter. That is scale. The big one is, okay, whole is that 10 to the power minus 10 meter. But the small is so tiny, it is about 10 to the power minus 14 meter. How much small that is, right? It's very small ball, and outside little bit bigger ball. In that outside, that is the just the space, and that in that space you can find the electron. Okay, so this is the typical atom. Now what the typical atom has, so in the nucleus, proton and neutron, and outside that you can find the electron cloud. Like that you have the electron. Okay, so you have the electron outside that region. So this is a typical atom. So atom is the measurement of the atom or size of the atom is about 10 to the power minus 10 meter, but the size of the nucleus is about 10 to the power minus 14 meter. That's the English. That's the neutron, the nucleus. Okay, so the nucleus is very tiny. It's about 10 to the power minus 14 meter, and the whole atom is about 10 to the power minus 10 meter, around that. Okay, some are small, some are bigger, but they all are around this. Okay, so that's it for today for this, and we will continue the atoms next day. Okay, if you have any question, ask me, and thank you so much.